I want to start off by defining two things that you're going to see everywhere. Log without anything written down here, with nothing written down there, just log by itself with something like that. We define that as, and remember the equals with the 3 bars means we are defining this right now. This is how we're going to define this. This is defined to be the logarithm base 10 of whatever it is. And so you, on a calculator, you will see a little key that says log. They mean log base 10. That's exactly what they mean. This is called the common log. A common log. Right there. Okay. Another one that is way more important and way more fundamental, and in fact, as we're going to see today, is really the only one you ever need, is this one. Ln.
Oh yeah, I've seen that.
Yeah. What is that? Well, it is defined to be the logarithm base E. We'll talk about that in just a second. This is called the natural log. And E, the base, E, it's not just irrational. It's not just an irrational number. It is a transcendental number.
Sorry?
Yeah, we haven't talked about what that is, but it is much like pi. In fact, that's probably the only other number that you know that's a transcendental. But pi is a transcendental number. And it is irrational, meaning that it has a decimal 2.718 to blah blah blah. It goes on and on forever. It has a decimal expansion that never repeats, never terminates, right? So it's an irrational number. But what's more is it is a transcendental number. And I argue, as do most math people, that this is the most important number in all of mathematics. Way more important than pi. There's no question that this thing is way more important than pi. It shows up everywhere in everything. Everywhere and everything. You've actually seen it before. I told you to graph e to the negative x squared before on a homework on Desmos. That's what this is, E. If we will talk about E at length, your book just kind of glosses over it, which is a huge detriment to you, because this thing, like I said, is, I'm going to say, the most important number in all of mathematics. It shows up everywhere. And so anyway, so this is the logarithm base E. In other words, it's the inverse of the function f of x equals e to the x, which is arguably the most important function in mathematics, or things like it, things based on this. We will get into this. We are going to go deep into E. But for right now, this is what we need to know. These two things, the natural log, and that's how I'm going to say it. I'm going to say, like, take the natural log of 5, and we're going to say, okay, take the natural log of 5. Or the natural log of x squared plus 2. That's what I mean right there. Now, to be really confusing, I'm going to be very confusing, is that this natural log is so fundamental that, in fact, mathematicians and math-based stuff, not physics-based stuff, but math-based stuff, refer to log without anything as the natural log. Like, they go ahead and define this to be log base E of stuff. Your book doesn't do that, so I'm not going to do it. Your book uses ln, but I've been writing this. There's only one log. There's only one log that really matters, and it's this bad boy right here. So, like, for instance, if you go, and we're going to do this right now, we're going to go to Wolfram Alpha, I'm going to show you. I'm going to do this real quick. Okay, so we go to Wolfram Alpha and we say, okay, let's compute log of 7. Okay. And you'll notice right here, it says, assuming log is the natural logarithm. So when you're doing math-based stuff, Wolfram Alpha is heavy in math, not so much physics. Log is assumed to be the natural log. And so your math teacher out of university will be using this for this, and your physics teacher will probably be using this for this. We are going to stick with this right here. We are going to stick with log without anything right there is log base 10 always. Natural log, which is log base E, is ln stuff. Good to go?
Hopefully.
Okay, cool. So, all right. Now we got that out of the way. Let's do a problem. Let's say your boss said, I need you to solve an equation for me. And you're like, give it to me. I've taken Algebra 2 with Justin Thompson. I can do anything. And so he says, okay, I need you to solve this equation. 7 to the x equals 4. And you stop and you go, well, first off, and this is what pops into my head, is like, if this were something like 7 to the x equals 49, that would be easy because I know that 7 times 7 is 49. And so I could say, oh, okay, that's fine. But this is kind of weird because I'm thinking, well, even if you were to plug in a 1, right? Like you have 7 to the x, and if I go 7 to the 1, well, that's just 7. And so, oh, that's even 4 is much less than 7. And so I don't know about you, but my intuition says, hold up, is this even a thing? Like, am I going to get any, is this junk? Like you know, let's just see. And so what I'm thinking, what I would do, say, well, let me just graph 7 to the x. Well, 7's bigger than 1, so it shoots up like that. It goes through here at 1. And when I plug in a 1, I get out a 7. Okay, so now I have my graph of 7 to the x. And we're saying, okay, we need some value of x that I plug into this, and I get out a 4. And so kind of like how we did when we actually graphed these guys out, we said, well, this is kind of like looking at the intersection of these two lines. And I could see, like, yeah, actually, there should be a solution here, right? It would be one thing if your boss said, solve this right here. And you go, well, wait a second. You're telling me that this function put out a negative number? No, there's no solution to that. That's not going to happen. But this is plausible, right? You following me what I was just saying about that?
Yes.
Okay. So this is plausible because I could see, like, yeah, if you start here at 1, like you plug in a 0, you get out a 1, and then it's a nice continuous thing. There's no jumps. Eventually, I'm going to have to go through the value of 4 before I actually get all the way up to 7. And so there has to be some value of x right there that actually makes all this stuff work. Another thing, I'm just going to take note, is it should be the case that that number that makes it true, that value of x, should be between 0 and 1. So I'm just going to go ahead and note that right now, that x, the value that we're looking for, has to be strictly bigger than 0, because it's not 1. It has to be strictly less than 1 because the output, well, that would give you a 7. So it has to be somewhere between there. Okay, so your boss gave you this, and you're thinking, okay, this is not nonsense. There is some number, and I've actually found a nice bound on it. There is some number between 0 and 1 that when I plug it in, it should give me out a 4. But what is that? Oh, man. Okay, so one thing is we could just, this is kind of what we've been doing. And as a matter of fact, I'm going to go ahead and write it out here. if I have a to the x, and then I take log base a of that, what is my output? Or what do I get? What is that? That's what I'm saying.
X.
It's just x, right? And that was what we're talking about. This is what we've been talking about, which is, right, logarithm is the inverse of exponent. And so if you, this says, take 7 and raise it to the power of x, how do we undo that? What do I need to do to both sides?
Take the
Take the what?
I'm sorry, I totally just blanked. Would you ask that again?
Yeah. So how do we undo 7 to some power? So like this is how we undo a to some power, right? We
Yeah.
undo it. And so how do we undo 7 to some power?
You take the log,
Mhm.
so you have log base.
Uh-huh.
Oh dear, yes.
Log base what?
Ah, I got rid of my paper. Hold on. Okay, whatever. Log base 7.
Log base 7
Log 7.
of both sides. The reason you did that is because log base 7 undoes 7 to some power. It's exactly the same thing as if you had, say, x to the 7th equals 4. You would say, well, I'm going to take the 7th root of both sides. And so there's your analog right there, right? And that's what you do, because that's how you undo that x to the power of 7. You undo that with a 7th root to get back your x. And you have your answer like that. This is just the logarithmic and exponential analog of that. You took 7 to some power, you undo it with log base 7, just like you undo x to the 7th with the 7th root, right? So, okay. So, and the reason you did that is so that, and I'm looking over here, right? This is just an identity. It just brings you right back to x, and you get this. And so, you tell your boss. All right, boss. There's your answer. I'm certain, and we can actually check it. Let's just check this real quick, like, because you're about to give this answer to your boss and you want to make sure you just haven't messed it up. So you go, okay, let's see. This says that if I take this and plug this in right here, let's see what I would get. We get 7 raised to the power of log base 7 of, oh, yeah. As a matter of fact, whatever I plug in there is whatever is going to come out, right? That's another one of those identities, right? A to the log base A of anything, let's call it Z, comes back to whatever it is, in the same way that the 5th root of something to the 5th just undoes it. And so you plug this ugly number in for x, and you get 7 raised to the log 7 of 4. Well, that's how you undo that, and you come back to 4. And you're absolutely right. This is an exact answer. It's perfectly true. There's nothing wrong with that whatsoever. But then your boss says, doesn't help me out. I need a decimal approximation for that. And you go, okay, do this right now. Pull out your calculator and find your log 7 key. Do you have your calculator out?
Yeah.
And are you seeing something that says log 7?
No.
No, and that's the problem. It's like, I don't know of a calculator that has a log base 7 key. Nothing does, I don't think. And so it's like, now your boss is saying, well, I need a decimal. This doesn't help me. I can't plug this into my spreadsheet. I need like 0 point something. And you go, oh man, what do I do? Well, this is what we're gonna do. Remember that nifty fact? What I said last class, I said that the most useful property of a logarithm is this right here, that when you take the log base b, I'm using b because I mean like any base, log base b of any number, let's call it a, raised to any power, let's call it z. It has this property, this very important property that we like, that I call exponents drop down. And so this is the same thing as I take my z and bring him down here, log base b of a, just like that. And so this is the property that we're going to use. And I really want to stress here that it doesn't matter. It could be any base. This could be log base 7. It could be log base 9. Could be log base 10. Could be the natural log. It could be any log that we want. And let's just start with log base 10, which we already said we're going to write from now on as just plain old log, right? So we're going to take another thing is we can take the log of both sides of an equation and the equation stays true. So that's what I'm going to do right here. I'm going to say, okay, my boss gave me this. Take the common log of both sides. So that's log of 7x, 7 to the x, equals log 4. And this is why this property is so useful, is because, right, we're solving an equation for x, meaning we need to get x by itself. How do you get x out of an exponent? Well, this is how we do it. We're going to take advantage of this nifty property right here to say, okay, well now this x drops out, drops down. And so now we have x times log 7 equals log of 4, like that. And this is why this is the most useful property of logs right here, is how do I get into that exponent and get that stuff out? Well, this is how. And now you have x times some ugly number equals some other ugly number. I just need to get x by itself. How do I undo x times a number?
Sorry, I'm still writing. 1 sec.
Yeah, okay.
Okay, what was your question?
Okay, so we're trying to get x by itself, and we have this equation right here. What do I need to do to get that x all by itself?
Would you divide?
Divide by what?
Log base 7.
There you
Or
go. Log of
base,
7. Yeah.
Log of 7.
Log 7. So yeah, I'm going to divide both sides by log 7. Log 7. That cancels that and gives me finally, I'm going to get x is equal to common log of 4. No, buddy, not right now. Common log of 7. And it turns, now you look at your calculator. Old, you do have a key that does that. And so here's some, I'm going to pull mine up on screen right now, and we're going to talk about some common pitfalls first before we just go and calculate this guy. So, okay, can you see this?
Yeah.
All right. So we want to calculate log 4 divided by log 7. So I'm going to go ahead and click. Can you see my cursor here as I do this?
Yeah.
Okay, cool. So I'm going to click on log 7. Now here's the thing. This is one of the reasons why I really stress writing the parentheses, is because we don't want to just now go divide by log of stuff, because that's not what we're trying to compute. What I wrote right there. Okay, give me a second, buddy. Here, I'm going to come back to here. What I wrote right there, when I wrote log, and it already gave me the left parentheses when I clicked it. If I go log 7 and then simply divide by, and then go log 4, I'd have to complete these parentheses. What I've just computed here is log of 7 divided by log of 4. That is not even close to the same thing as this. Buddy, please leave my book alone. Go on. No, leave it alone. And so we do not want to do that. This is one of the reasons I stress writing this thing like this. And we're going to put that into here. Okay, so what I have up there right now is wrong. We don't want to do that. I'm going to write it down the way that I've actually written it on the board, which is I hit log, and then I put 4 end parentheses. Now I'm going to hit divide and go log of 7 end parentheses. And that right there is what I have on the board. That is common log of 4 divided by common log of 7. And let's see what we get. Hey, look at that. That is a number that is between 0 and 1. So this looks pretty good. As a matter of fact, I'm going to go ahead, while it's up here right now, I'm going to write this here and go x is approximately 0.712414. 1, 2, I'll just stop at 4. We'll use 4 decimal places for now. And so I'm saying, okay, x is approximately that much. All right, so let's check that. Let's see, because what our boss asked is, I need to know what number I need to raise 7 to that will give me 4. And what we're saying right now is if you plug this number in back into the original equation, you should get out a 4. So let's see if that's true. I'm going to double check it and say, okay, 7 raised to the, and then the way we do that is we go up here to this caret, that little up arrow right here. I'm going to go raised to the, and this is a really nice calculator. So it actually like puts it up in the exponent. So that's nice. So 0. Point, I'm not going to use all of those, but I'm going to go 7, 1, 2, 4, 1. And let's see. This, because I've chopped it off, it shouldn't be exactly 4, but it should be close to 4. So let's see. Enter. That is very close to 4. Good. Now, if I wanted to, I could. I'm going to hit my up arrow key a couple times to get this guy back. Now I'm going to hit return or enter to get back there. Hit the back, and I'm going to put in a few more decimals and just see, like, did the answer I get, is this really doing what I want it to? So 71241, how about 437? So 437, enter. Yes, it's getting closer and closer to 4. It's kind of what I was saying about with the sequences before it, but don't worry about that. Like, it's getting closer and closer. The more decimal places I use, the closer that thing's going to get. And so I feel confident about this. So I'm going to get rid of this right now, come back to our screen. So I feel confident that this is an answer that my boss will accept, right? Like, and I've used this, not sure if you noticed this, I put a little dot over the equals to show that it's not just approximate, it's a measured approximate. Like, that means a little bit more than just the wavy lines. The wavy lines would be like, about 0.7, meh. But like here, I'm saying I'm approximating, but I'm using some precision here. Like I feel really confident about this answer, which I do because we checked it. So, okay, Great, now we know how to do that. But this is interesting though, because I just arbitrarily chose to use log base 10, the common log. What if I'd used another log? Does it work? Well, this tells me it would have worked. Let's test it. Let's see what happens. So I'm going to get rid of this right here. I want to hold back onto this because remember, I said this is absolutely true. This is 100% true that x is equal to log base 7 of 4. And so I'm going to have that up here too. That x is equal to log base 7 of 4. But I want to give myself some room here. Okay, so let's get rid of this right here. And before I get rid of this, let's just remember how we did this. This is where we started with our original equation. We took the common log of both sides, and then we ended up getting x in terms of common log right there. Okay, that's how we got that. And now, this identity or formula or whatever you want to call it tells us that it doesn't matter what base you use. So let's do the same thing, but instead of common log, let's take natural log of both sides. So I'm going to do that. We have an equation. I'm going to take the natural log of both sides of it. Okay. Why did I do that? Well, in order to get that x to drop out. I'm trying to get x by himself. The only way that I know to get x out of a exponent is to take a log and use this property. So x drops out. Log 7, natural log 4. And now x equals what? In other words, how do I solve for x?
Yeah, you divide by log 7 or natural log 7, I guess.
Yes. If you just say log 7, I know what you mean. Everybody knows what
Okay.
you mean. And that's, yeah. I'm going to be careful about saying natural log because, but like really, and like I said, and we're going to see in just a second, you only need one log. There's only one log that matters, and the natural log is the best one to use. And so, okay, we divide both sides by natural log 7. Log 7, and let's see what we get. It says that x equals natural log 4 over natural log 7. And we go, wait a minute, how could that be? Like this right here, that was the common log, which is log base 10 of this. How could it possibly be the case that, and so what we're going to do is check. We're going to say, well, wait a second, hold up. Let's go to our calculator. Okay, so apparently I could have done this with natural log. So let's do that. I'm going to plug in natural log. So I hit the ln key, natural log of 4, end parentheses, divide that by natural log of 7, end parentheses. And now I'm going to hit enter and see what I get. It's the same thing. Huh, interesting. This is another property of logs we're going to talk about in just a second, but we could see it really didn't matter which log I took. Okay, so, all right, and I'm just going to double check. Yep, 71241. Yeah, 4372. Yeah, okay, there we go. That's the same stuff. So, okay, let's get back to the board here. Well, we found a couple interesting things here. Like we'll get the same approximation, the same decimal approximation, whether we use common log or natural log. Another interesting thing we found is that log base 7 of 4 is equal to the natural log of 4 over the natural log of 7. It's also equal, and here, I'm gonna write this out to show you exactly what I'm talking about here. Like, okay, so before I erase that, let's just double check. Yeah, the x that we got was indeed between 0 and 1, which is what we expected. And we did see that when we plug this in, take 7 and raise it to this power, we do indeed get out a 4. So that's good. We are good to go right here. This is the really interesting thing, is that this number that we're trying to calculate, we called it x, which we said is exactly equal to log base 7 of 4. We could write that as natural log of 4 over natural log of 7. We could also have written it as common log of 4 over common log of 7. They're all exactly equal. And so this is kind of what I mean by we only really need one log. And it turns out, for reasons that we really cannot get into, the most accurate way of calculating things is with the natural log. Your calculator, the way that it's programmed, will give you a better approximation using natural log than it can with anything else. It's one of the reasons we call it a natural log, because it's kind of the log. Everything else is kind of natural log in disguise in a way, and you kind of see that with this right here. This brings us to an interesting principle, because it's like, well, I could have solved the original equation a bunch of different ways. And like, for instance, so this is how we started with this question. And we said, well, clearly you take log base 7 of both sides, and that will give you blah, 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 blah. But let's try to generalize this a little bit, right? Because it didn't necessarily need to be a 7 raised to the x and equals a 4. It could have been any base at all. As a matter of fact, that's what I'm going to do. I'm going to say, let's say it's any base at all, a raised to the x equals, and we don't want to do it for one specific value of an output. We'd like to know if we could do this between any two values. And so what I'm going to do is say, how about instead of 4, let's call it y. Okay. Then we said we could take any log we want, and to keep this general and to really drive this point home, I want to use log base b, which could be anything. Here you go, buddy. Sorry. And so I'm going to take log base b of both sides here. Say, okay. Well, I'm sorry. First thing I want to do is the very first thing we did, which is let's solve it like this. Let's get x by itself by just using log base a on both sides. If we do that, we have log base a to the x equals log base a of y. And remember why we did that in the first place is because that's exactly how you undo this, right? You took some number, raised it to the power of a, and so you said, oh, we'll take the 8th root of it. This is the exponential analog of that. We're saying take a, raise it to the x. How do you undo that? Well, with log a. And so that comes down to x, right? That's how you get your x back, equals log base a of y, right there. I'm going to take that result and write it right here. X is equal to log base a of y. So basically, I'm doing the analog here, but only without a specific base, like our original case was 7, and our specific output value 4. Here we're saying, well, it could be any base whatsoever and any output value that you care about. But then what I'm going to do, so let me know when you got this, when you're taking. Okay. So then what we do is say, well, hold up. We don't need to take log base a. We could have taken any log. In fact, we could take log base b of both sides. So let's do that. Log base b of a to the x equals log base b of y. So then we use our favorite property of logs, which is exponents drop out. And so we rewrite this as x times log base b of a equals log base b of y. Finally, we get x by itself by saying we divide. X is then equal to log base b of y over log base b of a. And we finally say, oh, and we've seen it already numerically, like, yes, these things are the same. If you plug that into a calculator, you'd get the same thing as plugging that into a calculator. And so, and we can see x equals x. And so finally, what we end up with is what we call the change of base formula for logarithms. And it's that, I'll go ahead and get rid of this guy right here. And since x is equal to x, then log base a of y is equal to log base b of y divided by log base b of a. And I don't know, I didn't see this in the book. This is very useful right here, right? Like, for instance, we wanted to compute log base 7 of 4 because my boss said I need to know this number. And it's like, well, I don't have a log 7 key. Well, one way of doing it is to say, well, wait a second, we could change the base. And so, for instance, if I'm trying, and this is how we would do this, we'd say, okay, the thing I want is log base 7 of 4. So I'm just going to kind of fill in the blanks here, right? And we could use any log we want. In one case, we use a common log because we have a key for it. So let's do that. I'm going to say, okay, the new log, that's the old base, goes to the new base. In this case, it's base 10. And so I'm just kind of filling in here. So what I've done with this is I've said, well, B in this case is 10, but we don't write the 10 there. We just write it as log. And then there's this one says, well, you take whatever your input to your original was and put it up here. Okay, so 4 was right there. And then whatever the old base was, the old base in this case is 7. And so the old base goes right here. Lo and behold, that's exactly the same thing that we got by actually solving the original equation. Common log 4 divided by common log 7 is the same thing as log base 7 of 4. It's more useful. We could extend this a little bit more and say, well, nobody cares about log base b. And Justin told me that the only log that ever matters is the natural log. And indeed, that's it. So I'm just going to rewrite this right here as natural log y over natural log a. And really, that's it. So like if I wanted to compute log base 3.1 of pi, what do I do? Well, I know that I could redo this by using natural logs. I'm just going to use some natural log over some other natural log. And what's kind of nice, like you don't really need to use your brain, is like which one goes where? Well, one of these is kind of above the other, the way that we write it, right? The base is a little bit below. And so you could just throw the lower one into the lower one. You take the higher one and plug it into the higher one. And so you get that right there. But it's very nifty to have this. And your book doesn't have it, but it is very, very useful because sometimes you just need to calculate this guy. And there's no bigger, broader context. Like our original context was 7 to the x equals 4, in which case, as we're going to see today, the name of the game is take logs of both sides. That's always going to be the case. But if this is your question, compute this, estimate this right there, well, then I could use this and say, okay, well, that's the same thing as this over this, and then blah, blah, blah. Okay, so questions before we move on?
I don't think so.
Okay. So, that boy lost my place. He just took my book and turned it to where he wanted to read. Okay, here we are. So, all right. I'm gonna get rid of all this stuff. Are we good?
Yes.
So. This suggests a method for solving equations involving exponents. So for instance, from 12.7, and yes, we are skipping 5 and 6 because you don't need to know any of that stuff. You'll never use that stuff. If you are going to take a standardized test in this kind of stuff, do look over 12.5 and 12.6. Though you'll never use that stuff. So we're jumping into 12.7, and here is an example from that. So let's look at number 2. Says to solve 2x equals 32. Now, here's the thing about this homework assignment that I'm going to give you, is that in this case right here with the 2x equals some power of 2, we can figure out what that is. 32 equals 2 to what power?
Oh, right.
Just start multiplying 2 by itself.
4, 8, 16, 32.
32, so 5 of them. Okay, now you notice how long that took? It took a while, right? Like and this is the thing, if you could use your brain, sometimes it's nice. And so in that case, I would say, oh, now if you really want to, you could operate on both sides. That is, we could take the log of both sides, right? We could say, in fact, since they have the same base, we could say, log base 2 of this. Log base 2 of this. Log base 2 of 2 to the is whatever that is. Log base 2 of 2 to the is whatever that is. And so x is 5. Or like from right here, we could see, well, the only way to make this equation work is if that number is the same thing as that number. And so we could have just said, oh, well, x equals 5. And okay, cool. There's a few different ways of doing that. Or we can not use our brains at all. We could save our brain, we could save our RAM for more interesting stuff, right? And we could say, oh, wait a second, I have the number I want, right? I'm trying to get x by itself. X is in the exponent. How do I get something out of an exponent? I take the log of both sides. Which log? The natural log. Now I'm going to go ahead and suggest this always use the natural log. So we're going to take the natural log of both sides. 2 to the x equals the natural log of 32. Why did we do that? Oh yeah, so that x can drop out. That's the whole point. Getting x by itself. Well, we already said, I want to have this up here. We already found out that x has to equal 5. And so I divide both sides by natural log of 2, and I get x equals natural log of 32, natural log of 2. In your homework, I'm going to ask you for both, when you do these, that I'm going to ask for both an exact form. This is exact. This is absolutely exact. This is what exact means. And an approximate. So that means we're going to have to go back to our calculator and plug that guy in. Let me know when you have this written down. Got it. So we're going to go to our calculator and let's clear all this stuff. So we want to find the natural log of 32. So natural log 32 end parentheses divided by natural log of 2. And let's see what it does. 5. Nice. And so come back here. Okay. And so x equals 5. Just like we found.
I have
Just
a question.
yeah. Mm-hmm.
When I take the square root of 32,
Is the square root of 2 to the 5th. Yeah.
okay.
Wait, but why? What about the square root?
Never mind. I don't know why I was thinking that. Never mind.
Okay, yeah, because we're talking about different things here, right?
Yeah, I was just on a. Yeah, never mind.
No problem. Yeah, so yeah, x squared equals 32 would be how we'd undo that. But this, yeah. So I really wanted to illustrate that, yes, like, well, this is the exact answer. And it happened to be that when I plugged it into the calculator, it gave me an exact answer. Oftentimes it will be approximate. Like I could have plugged that in and it gives me 4.999999997. It just turned out that my calculator is good enough with natural log that it knew, like it carried it all the way out and said, oh, it's all 9s. Okay, we're going to just call it 5. My calculator is smart. Some calculators will just give you 4.999999997. And so, that's what I mean. Like, so you will get in your homework, I do want to see both of these answers, right? The exact answer, and this one happens to be exact because your calculator is good, but we're going to call that the approximate answer, right? And so if your calculator spits out a decimal, that's what I mean, you know what I'm saying. So, okay, that's how we deal with those. And so like some of these, like you absolutely could solve, like this one, we absolutely could have solved it by saying, well, hold up, 32 is 2 to the this and blah, blah, blah. A bunch of them are like that in your homework. The point of doing it this way is so that we don't have to do what we did at the beginning and go, wait, 32, 2 and 4, 8, 16, 32. Oh, it's 2 to the 5th. We don't have to use our brain for that. We could save our brain power for more important problems. We could just say this, don't use your brain. You have an x in the exponent. How do you get an x out of the exponent? Take a log of both sides. And so that's going to be that is the skill that you are going to be developing for problems, or for your homework problems 1 through 5, is to get this, to just drill this into your head that, oh, when I see variables that I'm trying to get by themselves up in the exponent, the thing I need to do is take a log of both sides to do this type of thing. So questions before we move on?
No questions.
Okay. The next type of problem. So that's where your homework begins. The next type of problem that you encounter are equations involving logs. And one of them here, problem number 20, says log base 4 of x plus 3 plus log base 4 of x minus 3 equals 2. Okay, so when we had an equation involving exponents, we took a log. When we have equations involving logs, we're going to do the opposite, which means we're going to exponentiate. Problem is, it's just like if you had let's say you had an equation that looks something like this. The square, you don't need to write this down. If you had the square root of x plus 3 and the square root of x minus 3 equals some number, boy, that's going to get ugly because you would square both sides, but you'd have to FOIL this thing out. Yuck, right? And so the idea, though, when you have some kind of equation like this, is to get one root all by itself. And if you could get one root all by itself, easy, you just square and everything's fine. So like compare, no, Peter, please don't. So compare this type of problem to, say, this type of problem where the one root is all by itself. Well, that's trivial. You just say, Peter, please stop. Stop it. Okay. So this is trivial because you got one root by itself. You know how to undo a root. You just square both sides. And so you would have like x plus 3 equals 25 and you'd be done, right? The same thing is true here when you have logs in your equation. If you could combine this into one log, it's going to make your life easier. So let's do that way first. I'm going to show you not all is lost if you don't do it that way. But first off, log of something plus log of something, how do we combine those? This was in your homework.
It's gonna be the values multiplied, right?
Yes, whatever is inside of there multiplies. And so we get log base 4. And I don't know if I said this explicitly. It has to be the same base.
Yeah.
Right? And that should be obvious. Maybe not, but I mean, you should expect that, right? So, okay, so we have x plus 3, x minus 3 is the thing. Now, how do we undo log base 4?
X plus 3, minus 3. Okay, you do the oh boy. Then you have the base, so x plus 3 times x minus 3 equals. Oh wait, no. Hold on.
Wait, that's not what I asked. I asked you, how do you undo log base 4? What's the opposite of log base 4?
The to the 4th.
To the 4th, exactly. So I'm going to raise both sides of the equation to the 4th. I'm going to take 4 and raise both sides of the equation to the 4th. So the way to undo log base 4 is we really don't need to use our brains, right? As long as we remember that this is the opposite of 4 to the x, we just say, oh, 4 to that stuff right there. And I'm going to go 4 to that stuff right there. And so that undoes that, leaving me that right there. And this is why I was really adamant about, like, yes, your book says that log base 4 of something equals something is the same thing as some dumbass equation that you're never going to remember. Or you could just remember, how do you undo such and such? How do you undo squared? You square root. How do you undo cube root? Well, you cube. How do you undo log 4? You take 4 and raise it to that stuff. How do you undo 4 raised to stuff? Log 4. They're inverses of each other. So just take the inverse of both sides. And so that's how we make that drop out. And I'm not going to continue on with this. This is a quadratic. You go first, outer, inner, last. You get, actually, we could do that pretty easy because that comes out to that right there. Outer, inner cancel. 4 squared is 16. 9. Actually, we do need to go over this. And so x squared equals 16 plus 9, which is 25, I think. Yeah, 25. So we get x squared equals 25. Let me know when you get to this point right here.
Okay.
Hey, buddy. Okay. He is climbing on everything now. Nothing is safe with my boy. Okay, so we get down to this point and we say, oh, I know how to take a, I could do that. Solve for x. What do we get?
5.
Plus and minus 5. And here's the
Oh.
right now, and like if it were just x, right? If finally we had something like this log x and we did a bunch of stuff, then we'd say, yeah, it has to be positive. So we're not going to worry about the negative answer. But in this case, we end up with x squared equals 25. So that x equals plus or minus square root 25 or plus or minus 5. And now this is slightly more complicated. I'm not 100% sure that the positive answer is even going to work. Like for instance, if I got that x equals 2 right here, I would try to plug that back in and I would get x minus, or I'm sorry, 2 minus 3 is negative 1. Uh-oh, that ain't going to work. So we have to throw that answer out. And so when it's not just straightforward stuff, you can't just say, well, forget about the negative one or forget about the positive one. You always got to go back and say, hold up, wait, it's just like when we had equations with square roots. It's easy to say, oh, just throw away the negative answer. Well, unless the negative plus something actually turned out to be positive. So as a rule of thumb, when you have equations like this, don't just not consider one of the answers. Get all of the answers and then check every single one of them. And so that's what we're going to do. We're going to say, okay, we get a plus 5 and a minus 5. Plugging in a plus 5 here gives me an 8. That's good. Plus 5 here gives me 5 minus 3 is 2. That's perfectly good. But now, yes, you're right. You're right that the negative one is not going to work because I plug in the negative 1 here. I get a negative 2. Plug in negative 5 here. I get a negative 8. Ain't going to work. And so we're going to say, okay, finally, x equals just 5. We have to check all of the answers. Questions?
I don't think so.
Okay. Then things get funky. And I'm sorry, but here's one type of question that you're going to have. Okay, so number 22. Next even one. Number 22 says log of the cube root of x is equal to the square root, oh no, of log x. Oh no. Well, let's think about this. Now, this is a nifty principle that you'll probably want to do. The idea here is if I could get both of these things to be log of the same thing, right? Like for instance, log x, and if I could somehow turn, I don't know how I might do that, turn this into just pure log x, then I could say, wait a minute, and this is kind of like your question for 45 from your homework. It's like, I could pretend that log x is just a new variable, and I'll forget about the fact that he's a log until later on, and then I'll bring that back in. And so right now, that's where I want to head right now. It's like, if I could get these to be log of the same thing, then I can make my life easier. So that's the direction I'm going to go to. First thing I'm going to do is say, wait a second, let's rewrite that as an exponent. And so the cube root of x is x to what power?
A third.
A third. There you go. That's almost always what you want to do with these types of things.
Okay.
Is anytime you see a root of any kind inside of a log, say, wait a second, I could just pull that out if I could write it as an exponent. And so I took my cube root, wrote it as an exponent. Now I'm going to pull that exponent out using our favorite property of logs, which is that exponents drop out. And so we have 1/3 log x equals square root log x. And at this point you go, oh no, I have no idea what to do. That's when you say, wait a second, I have a log x and a log x. Let's just pretend for right now. Let's let log x equal y. And so I'm going to substitute right here and say, okay, because honestly, and even me, when I look at this equation, I'm like, I don't know what to do. I'm going to square it, then I'm going to have log squared equals, and it looks terrible. But so I'm going to make my life a little easier right now and say, okay, can I solve this equation? That ain't so bad. That ain't so bad at all, because like right now, no, I can't solve that. But I could say, you know what? The only thing that's really messing up my life right now is that square root. And how do I get rid of that square root? What do I need to do? Square. And so I'm going to square both sides. And so let's do that. Square both sides. You'll notice I didn't say, we didn't use some principle that y equals x if and only if y equals x squared. We didn't, you know what I'm saying? Like that same thing with the logs. I see an equation and I'm like, what can I do? What operation can I do to that equation to undo that thing? That's how you want to think about logs too. So when you see log base 4 of stuff, go up 4 to that power, undo it, right? Same way, square root of something, square it. Get rid of it by squaring it. So we're going to do that. A third cubed is a 9th y. I'm sorry. A third squared is a 9th. Y squared is y squared. That equals y. Okay. This is a quadratic. It's quadratic in y. And I'm going to rewrite that as 1/9 y squared minus y equals 0. I could use the quadratic formula if I were so inclined. I could factor it. I think factoring is going to be slightly easier by going 1/9 y minus 1 times y and that means that y is either equal to 0, put that up top, or 1/9 y minus 1 is equal to 0. 1/9 y minus 1 equals 0. And if that's true, I add 1 to both sides, and I get 1/9 y equals 1. Almost got y by himself. And we'll do that right now by multiplying both sides by by 9. Y equals 9. And so I get 2 answers. And let's see which ones we could do. So Now, my instinct is to say, can I plug 0 into here and here? Can I plug 9 into there and there? But oh, this is y. This is not x. We have not solved for x yet. We haven't found x. And so we have to come back to this guy. All right, tell me when you've caught up and you've solved for these guys.
All right, I'm good.
Okay, so now and get rid of this work right here and say, okay, well, I've solved for y, but wait a minute, log x equals y. Okay, so log x equals y, and we have two possibilities. It's either equal to 0 or log x is equal to 9. And now we could try to rack our brains and say, well, x would have to, if I plug in an x and get this, or we could not use our brain and say, how do I undo log base 10 of something? Because this is log, yeah, this is log base 10. They gave us, this is the common log, remember from the beginning of the class. And so the way to undo this is going to be to take 10 and go like that. That undoes that to give me an x. 10 to the 0 is what?
1.
1, so x equals 1. Same thing over here. I'm going to have 10 log x equals 10 to the 9, which means x equals 10 to the 9th power. Now I'm going to go and check those guys. I can plug in a 1 here. Cube root of 1 is 1. Log of 1 is perfectly fine. You can plug in a 1. Plug in a 1 right there. Log of 1, perfectly fine. Now 10 to the 9th. Yeah, I could plug that in there. It would be 10 to the 3rd. No problem. Okay. Log of that number. Yep, no problem. Again, I could do the same thing over there. No problems. And so I think we're done. Both of those work. Just remember, log here means log base 10, and that's how we ended up doing this to undo log of x. Questions, concerns?
I think I'm tracking.
Okay. Another thing I ain't gonna go into that. That doesn't matter. Okay, so we're almost done. We're very close to done here for today. Some of these get kind of ugly, but the principle is the same. And I mentioned this earlier. Didn't say it explicitly. That when we did the one with the log base 4 of x plus 3 plus log base 4 of x minus 3 equals some number, I think it was 2. Yeah. I said that we needed to combine those to make them the same. I didn't necessarily need to. I could have done it this way. I don't recommend this, but if you do, it's going to work, because I noticed, wait a minute, log base 4, how do I undo log base 4? Well, I take 4 and raise it to that power right there. And this is exactly what we did. And so we have that right there. And as long as you remember your properties of exponents, which is that a of u plus v is equal to a times a to the u times a to the v, then you could say, oh, wait a second, this 4 raised to the something plus something is the same thing as 4 raised to that thing times 4 raised to that thing. Equals 4 squared is 16. And yeah, 4 and 4, that cancels out to give me an x plus 3 times 4 and 4 cancels out to give me an x minus 3. Lo and behold, we have the same thing. So my point is, not all is lost if you do this, or if it's what's in there is really wicked, and when you combine them together, you get something that you just can't really wrap your head around. Maybe you want to go this route. Doesn't matter. Either way you do it is okay, but I recommend trying to get all the logs together so that you're only doing it once. And then you don't have to remember this weird rule, and just that looks terrible. Just personally, I don't like it. So that's the idea behind that. And I think that's pretty much all you need. I'm going to recommend, yeah, all right, I'll when I write down the homework, I'll say it explicitly. Any questions? Because we are pretty much done. I'm about to put up the homework. Any questions before I do so?
I don't think I have any questions.
Okay, it's pretty straightforward stuff. Just really get in. We're about to get kicked off too. Just get in the habit of thinking, oh, the opposite of log base 4 is 4 to the opposite of log base, whatever. And on the other hand, when you're working with exponential equations, stuff that doesn't have log with an explicit base, if you have x in the exponent, just use natural log. Natural log's best. Chapter 12, section 7, pages 147 through 8. Number 1 through 15 odd. These are the exponential equations, and I'm going to tell you to use natural log. Use natural log on these. And I want two answers. I want the exact answers. And so that's 1. I want exact answers. 2, then use your calculator with natural log, basically plug in the exact answer that you got with your calculator to get approximate answers. You know what I mean by that, right? We talked about that earlier. So an exact answer is log of 7 over log of 5. Okay. And so you gotta wait, buddy. Okay, then we are gonna do 5, number 17 through 25 odd. We are skipping all the word problems, but don't worry, we'll be coming back to the word problems shortly.
Great.
Yeah. Then number 39. This is actually kind of important. I mean, it's like one of the things, compound interest, which you're going to want to know if you ever buy anything ever. 39 through 43. We are not doing 45 because that one is just evil. 47 through 51. (47 through 51). And I think it comes out to like 20 questions, I think, total. And what I'm going to tell you is it's that one right there. They just say solve. It's actually, I guess it's just number 49. On number 49, use natural log. They tell you to use log base V. Don't do that. Like, you'll never do that in the real world, ever. You'll always use natural log. So let's always use natural log. So we didn't do any examples from these last bits from 39 through 51. But I think basically the idea is going to be, so you'll have something, I just, just let you do. If you have questions, just get up with me. I think it should be all right. So